Okay, this is part 2 of our discussion on boundary condition analysis, and in part 1 we reviewed the various types of boundary conditions that are normally applied to groundwater models, and specifically we are talking about the conditions we apply on the outer perimeter or the boundary of our model. Every side of your model has to have some kind of boundary condition applied to it. The default is of course a no-flow boundary condition, and sometimes we put on a head-dependent specified head or specified flow boundary condition as well. Now, as we choose what boundary conditions to apply, and in many cases this involves how far out do we extend our model, we have to be very careful when we're selecting those boundary conditions. They have to be appropriate for the site being studied. If you're not careful, you can lead to artificial calibration or a non-unique model, which is something we talked about earlier when we were discussing calibration. That can happen due to the boundary conditions you apply, and we'll look closely at that in this lecture. And this is a very common source of model error. I've run across a number of groundwater models in my career that just had flat-out wrong boundary conditions, leading to over-constrained models. And so it's important that we take a little time and dig into that. And in this part 2, we're going to get a little more technical and drill down into some of the mathematics we're talking about. So to guide this discussion, we are going to consider this hypothetical site where on the left we have a mountain range and on the right we have a river. Somewhere in the middle there's an industrial plant, and our modeling objective is to create a local scale model in the vicinity of the industrial plant to maybe simulate the design of a remediation system for groundwater contaminants. We're going to look at some injection and extraction well systems, and to do that we need a groundwater model. So what kind of boundary conditions could we use? If we're going to do a local scale model, we just want to do a model in the vicinity of the industrial plant. One possibility is that we could look at the heads evident at the observation wells, and assuming that the groundwater flows from left to right or from the mountain range to the river. If we look at those head contours, it might be tempting to say, well, what if we made a fixed head boundary condition, or a constant head, specified head, however you want to say that, coincident with these observed head contours, one upstream and one downstream, and then perpendicular to the headlines and parallel to the flow direction, we have two parallel flow boundaries on the north and the south ends of the model, as shown by the green lines, and these would be the two fixed head boundaries and two no-flow boundaries. And I actually have seen this several times in my career, people doing this kind of boundary condition for a more local scale model. And now that might seem like, hey, why not? So that red blob there in the middle, that's a contaminant plume that we're going to remediate. And so why not do this? Match the fixed head boundary to your head conditions on the left and right, and away we go. So let's drill down into the mathematics here. So if you were to look at a cross-section drawn kind of down the axis of the model like this, and look at that in side view, we have the bottom elevation. Now this could either be a lower bedrock or just a lower layer that is of lower permeability, whatever bottom we choose here. And then we have a fixed head boundary condition on the left and the right. And then, we have our head observations that are shown in the map. And, when we build and calibrate this model, we expect the heads to match our head observations. And so it's a really simple flow system from left to right. But what's going on here? So since this is such a simple system, and let me back up here. So if we're looking at, and we're going to assume that there's maybe a little bit of recharge, but mostly it's just water coming in the left and moving to the right. Since it is such a simple system, we can look at this in terms of Darcy's law. And recall Darcy's law as Q is equal to the hydraulic conductivity K times the change in head divided by the length of flow multiplied by the cross-sectional area of flow. And for our particular case, we have let's assume a constant hydraulic conductivity for the site. H1 minus H2 is our head loss as we go from the left to the right. And then L is our length of flow. The saturated thickness of this we're going to call T. And so the area, the cross-sectional area, would be T times whatever the width of our model is, and the width is the dimension perpendicular to the screen. And so that becomes, and Q is the flow rate as we go from left to right. So again, just a simple, straightforward application of Darcy's law here. So if we plug in our variables from this, and then let's look at each of these in a little more detail. So the length, the thickness, and the width, those are mostly geometric constants that are not going to change. You could argue the thickness will change based on the head, but it's not going to change too much. And so those are kind of fixed. The H1 minus the H2, the head difference, well, that's fixed by the boundary condition values you apply on the left and right. So those are fixed. They're not going to change. So what's left? So now we have the flow rate through the system and the hydraulic conductivity are what I'm going to call independent variables. Those are the things that can change as we solve Darcy's law. Well, we can solve it in either direction, right? Method one, you can specify a hydraulic conductivity and then solve Darcy's law for Q. And so that becomes the only unknown left. Or you could theoretically solve this equation for K. And if you know what the Q is, for whatever reason, if you had an estimate or knowledge of the Q, you could then solve for the hydraulic conductivity. Okay, so that's fairly straightforward. However, what is really interesting here is the distribution of the heads as you go from left to right is not a variable. So when you solve this equation, the model will produce the same head distribution regardless of what value of hydraulic conductivity is specified. Now, to illustrate this, I have built a model exactly in the same configuration and dimensions of this, and that is, if you go to the course schedule associated with my groundwater modeling class and look at the exercise associated with today's lecture, you will see a step-by-step review of that. And basically, if you build the model like this, you can enter any value of hydraulic conductivity you want, and you'll get this same distribution of heads. Now, what will change is a hydraulic conductivity, but you'll get the same set of heads. So this is a classic case of a non-unique model. And you can run that exercise and verify that. But if you have this, and the issue is because of the boundary conditions that are selected, a fixed head on the left, fixed head on the right, you're just going to get a somewhat linear decline in head from left to right. And it might not be completely linear based on, variations in the thickness, but it's going to pretty much just be a simple extrapolation regardless of the hydraulic conductivity used. So what do we do? So obviously this would not be a very useful model. No matter what K you put in there, it would calibrate. And if you think back to our discussion on calibration, you say, well, the problem here is you don't have a flow observation. And that is true. But it's partly because this is what we often refer to in the modeling world as an over-constrained model. It's because of the boundary conditions, it's constrained to one solution, and that's it. So how do we go about that? How do we avoid an over-constrained model, a non-unique model based on the boundary conditions? And we are going to talk about three general approaches for doing that. One is if you had some way of doing specified flow conditions. So instead of having a fixed head boundary condition at the two ends of the model, if you could somehow extend the upper boundary back to a no-flow boundary, either to an outcropping or a groundwater divide, then your model becomes way more sensitive to your hydraulic conductivity and your recharge. You would have to have recharge in this case because there's no water coming in through the left-hand side. You have to have a source of water. And so this would give you a much less constrained model. If all you have is specified head boundary conditions, or if you have, well, it depends on the configuration of your specified head boundary conditions, then it's going to be too tightly constrained. But this would free it up. However, it's still going to be non-unique until you can pin down some estimate of Q. And to do that, I say flow observation. You could also label this flow estimation. Clearly, if you have a stream gauge and a stream somewhere in your model, as we discussed in calibration, that measured gain or loss would then fix your flow budget. It would pin down your recharge and therefore the flow through the system. The only variable left would be hydraulic conductivity. If you don't have a stream, sometimes we can do tracer tests. If you have an upstream monitoring well and a downstream monitoring well, you can put a non-conservative tracer. Non-conservative means it doesn't absorb onto the soil particles, and then sample the downstream well to determine when it travels from the upstream to the downstream well. But these are pretty rare, and sometimes it can just take too long. So it's not very common, but it could be a way to estimate the flow velocity. And if you have one, if you have a large area, and maybe if it's not on your site, but someone has done a tracer test to give some kind of idea of the groundwater flow rate, that's better than nothing. And so again, if you do nothing more than come up with an estimate of a reasonable flow velocity or estimate, that is way better than nothing, because once you fix the Q, you've eliminated one of your unknowns, and the only unknown left would be the hydraulic conductivity. Another thing, and in our previous lecture, part 1, we talked about lateral inflow. So if you had this condition here, and maybe a lateral inflow through the side, or I guess we should go back to this one. If you had some estimate of how much water is coming in through the left-hand side, again, just even a guess would be fine. Or it could be a lateral inflow from mountain front recharge. That could really help pin things down. And so, here it is represented more graphically. If you just have either, maybe that right head BC is really a river, and you have an observed gain or loss, or be it gain in this case, excuse me, Or even if you were, instead of observed, it would be an estimated flow. That would pin things down. The best case scenario is if you had a no-flow boundary condition on the upstream side, or a specified flow, and then an observed flow passing into your head or head-dependent boundary condition on the right. This would be the one that's the most sensitive to your hydraulic conductivity, and where you'd have the greatest amount of confidence in your in your flow estimate. Now, having said all that, the bottom line there is you need to have either a measurement or some kind of estimate of the flow through your system, or your model's going to be pretty much worthless, because you could put any hydraulic conductivity in it and come up with any flow, and it would result in any number of flow rates. As you change the hydraulic conductivity, it changes your flow rate proportionally. And we don't want non-unique models, because they become fairly worthless as a predictive tool. However, we can't always come up with the flow rate either through an observation or an estimate that we feel confident about. And so another way to solve this is to do something called regional to local conversion. Sometimes it's called telescopic grid refinement. And so if we do have this case, there's no flow observations available, and sometimes we just don't have any strong head or flow boundaries nearby. And by the way, when I started this example, if we put a head boundary condition based on contours, that's not a good practice. You should only use a head or a head-dependent boundary condition where you have an actual body of water. Not an observed contour, if we can get away with it, with an exception, which I'll describe here in a minute. And so one strategy is to extend your model out to be more of a regional model, extend it out to where you can get more or better defined boundary conditions. So if you think back to our initial case, there was a mountain range on the left and there was a river on the right. So theoretically, you could go all the way back to all the way out to the mountain range, and all the way to the right to the river, and then maybe do a parallel flow boundary on the top and bottom. And the problem with that, one of the challenges of that is now you have to incorporate probably a lot more wells in your system. More hydrogeology you have to interpret, but even if it's an approximate regional model, it's better than nothing. And then if you calibrate that, once you have that done, by extending the model to where you have good boundary conditions, well-defined boundary conditions like I just described, then you have more confidence in that regional model. Once you've done that, then you can do this process of picking out a local encapsulated version of your local model, derive your boundary conditions, pull your K and your recharge and other model parameters for your local model from the regional model. And let me just show you an example. So this is a model that I worked up a few years ago as an example case. This is we've got a river. We've got 4 wells. We have the no flow. So there's a fixed head boundary condition on the top and the bottom, and we have recharge everywhere else. But what we want to do is develop a local scale model right here by this little red rectangle. But by first building this regional model and then solving for a hydraulic conductivity and recharge that calibrate this regional model, then if you zoom in on your local scale model, you can pick fixed head bound. You can notice how I've aligned that grid. So this red rectangle represents my region of interest, and these black lines represent the boundaries of my new local scale model that I'm going to derive from the regional model. And in this case, if I interpolate the head values computed by my regional model to get my head boundaries on the upstream side and the downstream side. Actually, in this case, this would be the upstream side and this would be the downstream side. The water flows from right to left. And then in the perpendicular direction, perpendicular to the head contours, we have our parallel parallel flow boundaries, I should say. And once we do that, we can basically use the regional model to come up with, again, our boundary conditions and our K and recharge. And now we can create a local scale model. It might look something like this. Here are our fixed head boundary conditions on the upstream and downstream side. And you might say, well, wait a minute. Isn't this still over-constrained? You have a fixed head boundary condition on the upstream side and the downstream side, both of which came from head contours. Yes, but we've already calibrated the regional model, so we have some confidence that our hydraulic conductivity and our recharge are reasonable. Therefore, we can use this kind of locally derived model with more confidence. And so that is the basis of this regional to local model conversion approach. There are even versions of ModFlow where you can encapsulate one small, a local scale ModFlow model inside a large scale regional model and build a connection between the two, so that if you make changes to your regional model, the local model automatically derives updated boundary conditions from the regional model. So you can do it manually by interpolating the head values, or you can have a more structured combination. But this, again, if you ever have to do a local scale model and you just are struggling to find boundary conditions, sometimes you have to just extend it out to the regional model. So let me just summarize this by saying picking boundary conditions in a real-world environment can sometimes be the most challenging part of developing your conceptual model and your numerical model. And you just have to really remember these concepts we've talked about and make sure that you don't have an over-constrained model, and then you should be in good shape. Thank you.